Don't we get started? Good morning, everyone. I hope you all had a good dinner and got to do some fun stuff outside last night. I know it was a long day. So hopefully some of you are staying and going to enjoy Alaska. So let's kick it off with our keynote talk for the day from Dr. Vipin Kumar. And I'm really excited about this talk. I joke with Vipin and Shashi all the time that I used to read their papers when I was a PhD student. So you know how much work they have done in this field. So Vipin, I'm going to embarrass Vipin a little bit. He has decades of experience, and I think he's looked at big data and climate change for many years through the expeditions, proposals. He's a AAAI fellow, a AAAS fellow, an IEEE fellow, and a SAM fellow, and I think there's more in there. He's published over 300 articles, 10 books, and done a tremendous amount of work in climate change in using spatial and other types of complex data. So with that, I would like to welcome Vipin and look forward to the talk. Thank you.
Again, thanks, Vandana, for inviting me here. It has been a great learning experience. I have been enjoying all the talks and all the interactions with people. So this talk is about, of course, this is a general talk I give at many places, and it again sort of talk about how the computing community, the machine learning community, the AI community can contribute to many of the environmental challenges our society is facing, and also in the process be transformed by in the process of transforming these challenges, be transforming the field itself. So these are the sort of the twin messages I like to give. So again, this is just to remind people that, and again, this is a message that's of course this community doesn't need to hear, that we have tremendous challenges that are facing the society because of climate change. And of course, this group is focused on as the globe warms, what happens to the polar ice when it melts, it sort of raises the sea level and makes people's life difficult. But as the polar ice melts, there are lots of other things happen. The more of the permafrost gets exposed, and that sort of leads to more global warming. So there are a lot of interactions like that. And of course, as we have already seen, some of the major effects of climate change already in our life, and they'll get worse as we sort of go on with time. But climate change is, again, one of the many interacting environmental challenges that faces the humanity. The other challenge that sort of faces us, how do we protect the planet? How do we keep it intact? Its biodiversity in the process of feeding an increasing population. In 2000, the population of the Earth was 6 billion. It has crossed well over 8 billion about a year ago. So as the population grows, and it has been growing, for the last 150 years, you have to feed more people. And one of the ways we have fed more people is by converting more of the forest into the farmlands. And you see the picture in the top right corner from Indonesia. You see the square box. The right portion of the box is dense old growth forest, Indonesia, and the left portion of it is the oil palm plantations, which have been sort of, it's a lot of these forests have been converted into oil palm plantation, for example, in Indonesia, sugarcane plantation or soybean plantation in Amazon, and so forth. As we're doing more and more of these, we're losing more and more of diversity. And if we run out of biodiversity, it sort of has a much broader implication even beyond climate change. The other thing is that so there's another challenge that's sort of happening at sort of perhaps at more immediate scale, which is the availability of water. The fresh water, as Vandana sort of mentioned yesterday, is very limited. Of course, and it's about 3% of the surface of the Earth is as water. And many of these water sources are being impacted both by climate change and by human actions, in the sense that some of the worst impact of climate change are going to be faced going to appear to us, impact us through water. And you can already see increasing frequency of droughts and floods. But even without climate change, humans in the development process are impacting the water bodies. And what you see here on the bottom right corner is the picture of Aral Sea. It's one of the It's one of the largest freshwater lakes, used to be one of the largest freshwater lake in Asia. And you see its picture in 1989, and 25 years later in 2014, a massive water body shrunk down to something smaller. And it happened because the water, this lake was being fed by two rivers, one from the north, one from the south, and the water was diverted for agriculture, and it sort of led to ecological disaster. And you might sort of say, hey, this happened in a faraway place and a long time ago. Perhaps it's not relevant. This same phenomenon is happening all over the world. When I gave this talk in Salt Lake City a few years ago, I showed them the picture of Salt Lake City. Salt Lake has lost more than half of its water for exactly the same reason Aral Sea lost its water. And the last challenge is that, of course, not only the water's availability is becoming less and less certain, but the quality is becoming worse as well. And the reason is one of the ways we improve our agricultural productivity without potentially using more and more forest for farming is to improve the productivity of the land. That is, you grow more food in the same amount of land, and you do that by a number of things. And one of them is by putting more fertilizer into it. And when you put more fertilizer into it, a lot of it get washed away into the lakes and rivers, and you see these harmful algal blooms in large lakes, and it creates big jet zones in the oceans. And as the oceans sort of nitrify, eventually, this is a much longer scale problem. The all life on Earth would have no chance to survive. But these fertilizer that we use to increase the productivity also actually emit a huge amount of greenhouse gases. And that's sort of what Shashi talked about yesterday as to how do you make agriculture, which is net positive for greenhouse gases, into sort of zero or net negative itself. So these are all existential challenges that are all interacting, they're all time critical. And the question you would sort of say is, what is a computer scientist doing, talking about on the podium about this? And the connection is, of course, through data. And of course, the data revolution has changed all aspects of our life. You sort of, imagine all the things that you're doing today and what, you would be doing 20 years ago, and that there's a big difference. And this revolution is fueled by three different advances in three different technologies: increasing amount of data, and increasing amount of computing, and increasing number of very smart algorithms. And there are three different circles. Each of them are playing an absolutely critical role. All of these revolutions have been going for the past 50 to 60 years. I'm not talking about last 10 years or last 20 years, at least 5-6 decades. You can sort of see the growth has been exponential, but we are really hitting the knee of the exponential growth curve now. So today, no matter who you are, you're being impacted by it. So it's changing us. And increasingly, the scientific communities are beginning to look at this new methodologies, machine learning, AI, as a potential solution to the problem. And again, this is what led to the Harnessing the Data Revolution program at NSF about 7-8 years ago, which is how this AGI institutes were established. And I'm just showing you these two pictures from Science and Nature, just to remind you that this revolution is not 5-year-old or 10-year-old. These pictures are 14-year-old. So even in 2008, 2009, people were thinking in the scientific community, that, and you're looking at the front page of Nature and Science, that this is really important. It's just that the urgency has increased, the acceleration of developments in all the three areas has increased. 15 years ago, NVIDIA was a small company, relatively speaking. Today, NVIDIA is the biggest company on the planet, and it's because that sort of led to that's the HPC thing you're saying here. But NVIDIA would not be as big as it is today if there were not better algorithms and not larger amount of data, and vice versa. So everything sort of comes together. So it's amazing to be living in a time like this. It's also humbling to be living in a time like this when you have such major challenges. And it's also an opportunity for us to sort of think together as to how we could work on some of these things together. Right? So given that there is a tremendous interest in using this technology in scientific problems, and of course, each scientific community is sort of using machine learning and latest methodologies from AI in addressing their problem. The question is, where are we? Are we sort of there? Are we sort of could AI solve the problem? You could sort of even hear even in any community saying, hey, could the foundation models do everything? Could ChatGPT do everything? Or could AI do everything? Right? This sort of tries to sort of bring you back onto sort of a status check in the sense that some of the biggest successes that you have seen for black box machine learning algorithms is in areas where there is a lot of data, but scientific domains have a lot less data. I think there was an example, there was a graphic yesterday shown illustrating exactly this point. The other thing is, no matter how smart these algorithms are, or however impressed you are by the capabilities, they're just crunching numbers, trying to find patterns. They're amazing algorithms. They can find nonlinear patterns of the kind that you could not imagine finding before, but they're still finding patterns in the data that you feed them. Yeah, there's nothing more than that, which means they have no understanding of the science, basic science. That means they can create scientifically inconsistent results. They would fail to generalize to unseen scenarios. There's a lot of discussion on that in many talks yesterday. And as a result, people have seen these algorithms failing in unpredictable way, right? And I'll have two examples here. The Google's Google flu trend, which was actually put in place about 12 years ago, because Google could look at they were able to build a model that simply looked at the keywords typed for Google search and use them to predict the outbreak of flu 2 weeks before CDC would announce. That was pretty impressive. That is, CDC takes so much time, they know so much, and yet they take them 2 weeks. But they have the pulse on the people, what they're thinking, and they could make prediction that, oh, the flu is coming, right? No, and 2 weeks earlier, right? But that model was built in 2012. In a couple of years, the model went completely out of whack. So we'll have to abandon. Same thing happened with the foundation model that Meta put up, for the scientific community, and then it sort of didn't survive very long. And in the non-scientific domains, when you're trying to look for advertising, when you're trying to make people click on the right ads or book the right hotel and so forth, the chances of failures or the cost of failure is very little. Now, a company can send you million advertisements, and if only 10% of them or 1% of them people click, others don't click, it's fine. Okay? But in the kinds of application we are talking about, a failure, the incorrect classification, incorrect results can actually can be matters of life and death, right? So these are much serious. So given this situation, let me see. Okay, how do I? Okay, yes. So given this state of where we are, we're looking at two different paradigms, right? A traditional scientific paradigm, which builds on our first principle-based understanding of the physical world or biophysical world or biophysical chemical world. You represent it in terms of equations and programs and methodologies. And then if those models, of course, are good, you're happy, you can get good results. And of course, as this community would know, that in most realistic scenarios, no model is perfect, and imperfection in the models leads you to not as good results as you would like to. So this is one thing. That is, if you have better and better theory or better understanding of the phenomena, better and better way to model it, you could be okay. But because of your inability to represent the phenomena at the right level of detail, because of computing power, or because of lack of your understanding or lack of data to be able to represent that phenomena, you are limited. So this is limitation of this traditional paradigm. The other paradigm, of course, is the current paradigm that has excited everybody about AI and machine learning, and that's driven by data. And these programs do exceedingly well. You have a lot of data, okay? And you can sort of see that in language modeling applications. 40 years ago, 45 years ago, when I was a graduate student, DARPA had actually disbanded the language translation program after investing tens of millions of dollars into it, saying, hey, look, we keep bumping money and nothing happens, right? And now, of course, gradually, again, many levels of improvements happen. But about 10 years ago, new advances in machine learning led to much better way of doing translation. And then again, 7 years ago, transformers came in and they really transformed the many aspects of language modeling. So if you have lots of data, then you don't need any linguistic information and you can really get to where you want to go to. But in most cases, you don't have the kind of data that you had in the language modeling. And as a result, you get the brunt of being not being able to generalize to scenarios that have never been seen before. So we have these two dichotomies. Neither of them is satisfactory by themselves, certainly in the scientific domain. So this is what sort of brings us to this exciting area in which you're trying to build a new generation of machine learning algorithms or data science algorithms that are driven by scientific knowledge. So the idea is that there are algorithms that become really smart. We don't, which have driven the successes in data science models. And if you give them enough data, you could ignore pretty much everything. You could have do knowledge-free learning, okay? But you don't have that luxury. But how do you combine the smartness of those algorithms together with the scientific knowledge that the communities have built over decades and centuries, right? Why would you leave that just and look at the data, right? And this middle paradigm is all about bringing them together. Sorry about that. So how do you bring them together to sort of make advances and actually limit the failures of both of these paradigms? And some of the, and again, as we all, as this community would know, the data and scientific applications are governed by laws of nature, and like conservation laws and such, but many other information that we have about the system that we're trying to analyze. And if you put them together along with the latest advances in machine learning, you have a new powerful paradigm. Okay? And this topics, of course, has been referred to sometimes if you're dealing with the physical domain, physics-guided machine learning, physics-informed machine learning, and so forth. But we are looking at this paradigm as more general, and it's driven by scientific. Okay? This paradigm, of course, emerged over let me see. Yeah, this paradigm actually emerged over over about almost 10 years ago. Shashi mentioned the expedition grant that we had at the University of Minnesota. And it's interesting, in the process of one of the projects we were working on in that grant was being able to model the ocean circulation and the eddies that are sort of moving around in the ocean. And that was an extremely challenging problem for the oceanography community. And being able to build a machine learning framework that could sort of look at the altimetry, the highly imperfect data, and how do you build those ocean eddies tracks required a merging of a lot of scientific knowledge and of course machine learning algorithms. So there were many such examples, and I'll share a couple more later on. They sort of led to these papers that we sort of started writing almost 10 years ago, and then it culminated with this 2017 paper about 7 years ago, which was a comprehensive article sort of saying, how do you bring these methodologies together? And again, it has sort of really, the field has really moved on since then. And this topic of knowledge-guided machine learning is a hugely growing community. There are lots of workshops over the last many years. There's a book on it, and there is this NSF-sponsored workshop on AI-enabled scientific revolution that we held at NSF's headquarters last year. And again, the whole paradigm, the whole premise of this workshop was that all of the advances that you see currently that are coming in from AI are driven by two applications, computer vision and language modeling. And these advances are being used in every other scientific applications. The question is, how could we think of a future in which the AI revolution is enabled by the needs of the scientific problems, and those revolutions then further revolutionizes the scientific discovery. So this twin synergistic relationship between AI and scientific problem is sort of what KGML is about, and that's sort of what this talk is sort of trying to bring you to focus, right? So when you're trying to bring a scientific knowledge and traditional machine learning paradigm, what are the challenges that you're trying to address, and what are the opportunities that you're trying to exploit? So on the left side of the screen, you sort of see the kinds of challenges that you would sort of say as a physical scientist you would face when you're trying to work with the problem. Well, I don't have enough data. Okay? We heard about that quite a bit yesterday. Okay, because observation data that you can use to build the models are not that many. The other problem that everybody faces in the scientific community is that there's the phenomena is highly heterogeneous in both space and time. That is, a model that works in a small one region may not work somewhere else. If you're trying to model any phenomena, it may work in certain portions of Alaska, but it may not work in Texas, right? Hydrology next Texas is very different than hydrology in Alaska or in Oregon and so forth, right? So if you build a model in one place, and if you are a computer scientist, you would use cross-validation to show that it works, and then you'll claim, hey, I built a model, you should use it, right? It gives you better result. And you sort of say, well, I take it to a different place and it doesn't work. And I can't, a computer scientist won't be able to tell you that because they only could look at the data that they were given, right? So this is a huge problem unless you handle the ability to generalize to scenarios not seen in the data. Machine learning, no matter how fancy it is no good for you or no good, and you shouldn't be trusting it, right? And again, the other thing is, as I mentioned earlier, that every advance that you have seen, nearly every advance that you have seen is driven by computer vision and language modeling. But the kinds of phenomena that you guys in any scientific community is trying to model is trying to model processes, complex processes that are interacting at different scales in both space and time. There could be soil cycle, there could be a water cycle, there could be a chemical cycle, they're all sort of trying to work with each other. You're trying to model them in the nature. And none of them have any analog in computer vision or language modeling. So we are trying to sort of take a square peg and then try to try to fit something else into it, right? So they're doing reasonably well. That's why everybody's still excited. But imagine how much more could you do if you really understood what this underlying phenomena are. And the other thing is that unless you understand what's going on, unless you have a good understanding of what your models are and why they're working, why they're not working, you shouldn't be trusting them, especially in cases where you're dealing with, life and death and all, or the well-being of the society, of the humanity on a large scale. On the right side is what you see with a broad brush, four major categories in which scientific knowledge and machine learning comes together. And whether you know it or not, I could take nearly every talk from yesterday and put into one of those categories. But by nature, the people are trying to fit their scientific knowledge into machine learning, right? Without knowing it. But looking at this in this format, you sort of get to see very easily, oh, number one, what am I doing relates to what everybody else is doing, and what could I learn from somebody else and advance my own direction, right? So one of the most widely used method in bringing scientific knowledge into machine learning framework is the loss function. Because if you train the latest neural networks, you're trying to perturb the weight of the neural network to make sure they make a prediction that is good for you, right? That you like, that you sort of is consistent with what you're trying to predict. And if it doesn't match what you're trying to predict, you perturb the weight, which is the whole paradigm of the gradient descent, and which sort of brought us to this current revolution over the last 70 years. But then you can add scientific knowledge into the loss function. There was a pretty involved discussion yesterday on this topic, right? Somebody was talking about PIN, the physics-informed neural network, and then saying, hey, I can take the PDE loss and put it into it. And then, of course, I can have multiple losses. And there was a question, well, if you have multiple losses, well, how do I do it? But the answer was, well, each of these losses are of different nature. You can't just add them up. You have to have hyperparameters, and you learn that. So all sorts of issues come up. But the bottom line is there are many, many ways the scientific knowledge can come into a loss function. There are challenges that come in, but there's a very rich set of literature here in this direction where you can learn from. If you're working on your problem, bring in your scientific knowledge, and if you can bring it into a loss function, you have a very easy way of incorporating into a machine learning framework. And second one is being able to initialize these models so that they are primed to get to the final solution much more quickly than they are. This is exactly the reason the foundation models, the likes of ChatGPT really works, right? And of course, either you in this case, if you have massive amount of data, then you don't need to initialize, you work with it, you train with the data, but oftentimes you don't, so you initialize the data. And in physical modeling applications, even if you have very little amount of data, you could use simulation synthetic data to initialize, and they can do wonders. The other thing, you heard a little bit of that yesterday too, self-supervision as a solution. And that's, again, a smart way to initialize. And all of the self-supervision methodologies that people have built in AI are driven by applications in, again, computer vision and language modeling. But in the scientific domains, there are so many more opportunities to bring in that information, right? And it's a very, very second area, is an extremely rich area for bringing scientific knowledge into the framework. The third thing is exactly where it takes a big departure from whatever people have learned in this area, and trying to figure out exactly the interacting structure of the processes and how to incorporate into machine learning framework. It, that, that, that for knowledge-guided architecture address all of these concerns, but much more so the ability to model complex and interacting processes. And then there are fewer success stories, but increasingly number of them that are really powerful. And you'll see some of the examples later on. And of course, there's this very large category in which you sort of try to both bring in the physical models and machine learning models in a hybrid fashion to work together. Okay, I could give literally a long talk on each one of these topics, right? So, but this is supposed to be a high-level overview. Okay, so in the rest of the time, I have about 15, 20 minutes, given that we want to leave some time for questions. I'm going to just focus on a sort of a narrow subset of scientific problem. And the subset that I'm dealing with is an environmental systems. And the system that you're talking about is, you see the circle in the middle. It could be any component of the environmental system. It could be a watershed, it could be a lake, it could be an agricultural farm, it could be a region, a farming region, it could be ice a sheet that you're trying to model. Then the system, environmental system, is being impacted by some drivers. Drivers mean something is changing its behavior. It could be the physical drivers, could be the weather, temperature, precipitation, could be greenhouse gas forcing. You may be interested in its response. You could, if you're a hydrologist, you could be trying to figure out the stream flow to understand the water cycle. If you are an ecologist, you're trying to figure out what the temperature profile of your lake is or water is. You could be looking at the greenhouse gas emission or sequestration. Shashi talked about it yesterday, and then so forth. So what you're trying to study is sort of part of your domain for the system. The system they're trying to analyze has drivers that impact its behavior, and the relationship between response and the drivers is often determined by characteristics of the system, underlying characteristics of the system. Some of them are observable, some of them are not, but they're there, right? And for example, the characteristics could be land cover, could be soil, could be how you're managing the soil, and so forth, right? If you're agriculture, are you irrigating the land? Are you using too much fertilizer, too little fertilizer, or whatever, right? There are all sorts of characteristics that one could think of that would build a relationship. And increasingly so over the last 5 decades, I just like to remind people that data revolution didn't happen within the last decade. It's going on for 60 years, is you have the ability to watch these systems at increasing level of spatial and temporal detail and spectral detail from all sorts of sources, including satellites and drones and planes and sensor that you put into the ground, right? So you have the system, it's being driven by something, you're interested in some responses, you know some characteristics, the relationship is influenced by some characteristics, you know some of them, you may not know some of the other ones. And this behavior is being observed through some external measures. And the question is, given this scenario, how do I improve the modeling of the system? If I could model it better, I could provide better guidance to the policymakers, I can give better guidance to the first responders and all and so. And I'm just going to give you illustration of this KGML methodology in the context of, for much of the rest of my 10 minutes. I'm going to talk about it in the context of 2 environmental systems. One of them on the left side is the modeling of flow of water into a stream. It's called stream flow modeling in response to weather in a hydrological catchment, which is on the left side. And the right side is being able to model the dynamics of temperature profile of a lake as the temperature changes. And of course, the hydrological cycle is critical for so many things, including, of course, what people study here. And the lake ecology is extremely important because the temperature is the master variable that determines whether the lakes are going to be healthy, what fish could be native versus species, and whether the and all sorts of things. So these are, and these are the works that are sort of being done in collaboration with mission-driven agencies like USGS, NOAA, and others. So basically, the physical scientists are involved, but also the mission agencies are involved very, very closely in this work. And one of the things that scientific modeling looks for is being able to create forward models. That is, if can you tell me if given the changes in the drivers, what happens to the response? Right, the forward model. And of course, you do that by building equations-based, first principle-based physical models. But as we talked earlier, the models can never be perfect. They have parameters that have to be calibrated. We'll say a little bit more about it. And the machine learning then comes in to sort of say, hey, give me a lot of data, and I'll just build a model for you, right? So that the forward modeling is that part. Okay? And sometimes you're building forward model to improve the ability beyond the physical model. Sometimes you say, I know the equations, but I can't really compute them at the level of detail I like to compute. So then I build an emulator, right? So there are all sorts of combinations that people sort of think about for the forward. Then there's the inverse modeling, and you heard a little bit about that yesterday as well, in which you are sort of given the drivers and the response, and you're trying to figure out what the characteristics are. And then, of course, you will see examples of forward modeling and also forward and inverse modeling working jointly to solve some problems that are very, very hard to solve otherwise. Okay. Now, this is sort of perhaps the most technical slide in the presentation. But I'd like to make a number of points, summarize from the previous one, and also sort of serve as a foundation for the future. And again, I'm taking the caricature of this hydrological catchment, which you see at the bottom. And if you're trying to model it using the traditional physics-based model, you will sort of assume, well, there's the water that falls. Some of it perhaps gets evaporated because you have trees or crops being grown in the catchment. Some of it might get absorbed by the soil. And how much will get absorbed by the soil would depend upon how absorbent the soil is at different layers, right? So, and the rest of it will probably go into the river. I'm simplifying it, oversimplifying it. But one thing I wanted to sort of say is that suppose I'm trying to model the soil. Now I can sort of say, well, I have the soil. I'm going to assume what fraction of the water gets absorbed by the soil. That could be one way, but really soil could be different at different layer. So I could make multiple layers in my physical representation and say, well, I would need to estimate the quality of soil at different levels. Now, as I do that, each of those things become parameters, theta, in the model. And then those parameters, like what is the capacity of soil to absorb water at different levels, each of them becomes a parameter. And as I try to make my model more and more accurate, I create more and more layers. Okay, but then I have more and more parameters. And if I simplify it, I have less parameter. But then I may not be able to model a system in which the model soil quality really changes from place to place, right? So this this is sort of an illustration of how when you're trying to build a model, even if you understood the hydrology, but when you build a model, you may be missing out some physics. If you assume the soil is the same at all levels, then you're missing physics. If you assume soil is different at different levels, you're making it more complex, right? So if you have missing physics, you have inherent molecular bias. If you make it too complex, I have a lot of parameters that have to be calibrated. Calibration happens to be computationally expensive, but if you forget the computation part, it's just the parameters can easily overfit for the same reasons as machine learning models overfit, because you're looking at some observations, some drivers and some observations, using them to figure out what model parameters will give you the right result. And this problem of overfitting is called equifinality in the scientific community. So that's one problem. But the biggest problem, and I'm going to come back to it later on too, which is traditionally, in machine learning, you don't know how to go out of sample. And physical models, the biggest problem is that once you build these models with lots of parameters, and if somebody gave you a lot of data for a specific catchment, if you instrumented a catchment, you found everything, you drilled the hole into the soil, you figured out how many different levels are, and you got all the values. But all that information that you're doing to improve the modeling of one catchment does not apply when you go to a different catchment. The physics transfers, but the parameters don't. Okay? The physics hasn't changed from one place from Texas to Alaska, but the parameters that you learned in Alaska don't help you anything as to what happens in Texas. Right? So that's the biggest problem. That means you could be collecting a lot of data in some places, but doesn't help you other places. So one of the all the red text is telling you about what is wrong with physical modeling. What are the limitations of physical model? And one of the biggest limitation, and of course, all of these are the limitations that are addressed by the KGML model. Right? So now the KGML model has the potential to deal with sparse observations because we bring in physical knowledge. We can generalize to unseen scenario because of being able to use the physical knowledge, but also being able to handle this inefficient use of the observation. They can produce physically consistent results. And the biggest power that I'm going to sort of show you is the fourth line. That is, if you have a lot of data in some settings, this framework can make it easy to go to other scenarios where you have no data or some data. So this ability to sort of leverage the data efficiently is unique to machine learning. And of course, KGML leverages that in the KGML framework. So these are all the points. I'm making a lot of points here. I'm going to show you a slide each to illustrate some of them in literally a few seconds each so that we have time for questions. But each of them, you will sort of see references to papers and you can sort of go back and study them, right? So this one this was as we started on this journey beyond our expedition, we wrote that paper I showed you earlier, the large team, Shashi and I and many others. And that paper was read by, by somebody at USGS. They were located in medicine, and they started making literally quarterly trips to Minnesota. They brought their whole team. Okay, and so this is the beginning of that KGML work in some sense to the scientific application. So their headquarters in data science headquarters in Midwest was located in the University of Wisconsin campus, near University of Wisconsin campus on Lake Mendota. So Lake Mendota is one of the most, because of that, Lake Mendota is one of the most widely observed lakes. Literally, they have observations on that lake at different depths going back well over 3 decades. So they sort of said, let's see how this paradigm works in this lake. So this is Lake Mendota you're seeing here. You're trying to model the temperature dynamics at different levels of the lake in response to the weather. And by the way, USGS does it for a living. It's a mission-driven agency. They have responsibility to keep track of how, responsible to figure out how the temperature in these lakes is being impacted by human actions and climate change for 185,000 lakes, right? Now, this lake happens to be the most observed one. Of the 185,000 lakes, they have data only for about 12,000, nothing for everybody else, right? And you're going to sort of see how this KGML paradigm really helps solve this problem. So here, they sort of said, we have a model called GLM, a generalized lake model. It's an operational model. It's used around the world. And if you have more data on the X dimension, you can do better calibration. And as a result, your error goes down. If you go to a direction, performance improves because the RMSE error goes down, right? So, but it's saturated eventually. Now we built a black box machine learning algorithm, traditional LSTM. It's something that an undergrad student in computer science would have done after taking the introduction to machine learning class. And it sort of says, hey, if I have a lot of data, I can actually do better than the physics model. Okay? This is how you would see some of us in computer science telling you, hey, we don't need your science. We just give us the data and then we'll get you better than that, right? Okay. But in this particular case, of course, they knew that they were trying to understand what's happening. But this one, of course, they knew is useless because for the amount of data that you have for Lake Mendota is available only for about half a dozen lakes in the US, that level of detail, right? Okay. Now, but if you put these two paradigms together, and I'm giving you a very high level summary here, you get the purple line. The purple line is learning from the imperfect green model and a little bit of observations. And even with a couple of days worth of observation, it can just get nearly impressive performance. Right? Okay. So that's the first demonstration. That is, yes, you could combine scientific knowledge and machine learning and break the barrier of very, very small data. This is a result from 2017, right? Now, this one is much more impressive. This is sort of saying, hey, look, how about going out of scenario, completely out of scenario? And then we did multiple experiments here, and this is the most shocking experiment. And here the idea is that you need data to calibrate physical models. You need data to teach machine learning models or KGML models. What if we hide some data? What if we hide summer data and only give it the fall, winter, and spring, right? And summers are, of course, beautiful, just like here in Midwest, summers are beautiful. Fall, winter, spring are very different. That means you're differentiating something quite a bit, right? So you see the green, which is the physical model. It also drops, even though the physics doesn't change, but the data to calibrate came only from the 3 season, not the summer. So in the summer, it performance became really bad. Machine learning model, which is the orange one, it drops like a rock because it has no clue as to what happens in summer in Wisconsin, right? But the KGML model, purple, was very resilient, right? So again, a big example that yes, you could, if you combine the two, you could go farther. And again, I'm giving you illustration from 7 years ago. These things have been repeated in many, many, many other applications elsewhere. This is just showing you that you can conserve energy. I don't have time to go over it, but it's literally trying to figure out exactly how much energy, what is the flux of energy in and flux of energy out. And the difference should really correspond to how much lake warmed up or cooled down, right? Now, since I have only a few minutes, I want to talk about this last example of being able to go from highly observed entities to unobserved or poorly observed entities. So this is the unique power of machine learning. And this is the unique weakness of process-based models, right? Okay. So I want to explain to you what this setting is. So in the top left corner, what you're seeing here in the green boxes is entities. Entities could be catchments or lakes or anything else that you're trying to study. For each entity, you have a data from certain duration. Let's hope enough duration that you could calibrate your models, right? And if you could calibrate your model, you can go into the future and then do good prediction, right? So going from green to yellow, a physical scientist would sort of say, I know how to solve it. I go to an area, I collect a lot of data, I can build a complex model, I can calibrate it, and I can go into the future, which is why areas that are highly observed, people can have good hydrological observations and make prediction to the future, right? But the real problem is being able to go to entities that are highly unobserved completely or poorly observed, very, very sparsely observed. How do you go from the upper to the last, right? So the machine learning, then I'll show you examples of how do you build frameworks that could actually do this really, really well. And again, I won't be able to tell you what the frameworks are because of lack of time, but I'm going to show you concrete results on a very, very large scale. So I mentioned to you, USGS is responsible for 185,000 lakes, monitoring 185,000 lakes. They have data for only 12,000. Okay? So using this framework, which I very highly summarized in the previous slide, right? We were able to build, this is Jared Willard, the first author of this paper, is a PhD student in computer science, many of the people, just like many of the people sitting here. So here's the guy leading the team with people from USGS, right? To build this first of a kind data set for the entire US to sort of say, hey, ecological community, now you know what's happening to all of your 185,000 lakes because of this methodology, right? So this is like a result that sort of has gone through the process of validation and acceptance by a very large community, right? The next one, another example, being able to figure out as Shashi mentioned yesterday, we are going to zero carbon future one way or the other, right? Okay. But how do you make sure everybody's doing it? Well, then you got to measure the carbon emissions. And one of the ways is you figure out what the GPP is, at the gross primary product at different places. And a really good way to do it is to put flux towers. Now, if you put a flux tower somewhere, eddy-covariance tower, somebody talked about it yesterday as well, you can get a very good measure of the carbon emission. But you can put flux tower here and flux tower there, but you can't put flux tower everywhere. There are only about a few hundred flux towers around the world, maybe less than 1,000, something of that. And you see the locations here. But how do you figure out what else is going on everybody's else? So this methodology in which you build a model in highly observed locations and take it to unobserved locations, right? This methodology is being used now again by the physical science community to build such models and transfer information. And there was this paper last year, just about a year ago, July of 2023, in Nature Scientific Data, not by us, by a different group at Columbia, which sort of use meta-learning approaches, approaches that allow you to go from highly observed to unobserved entities to model carbon flux from sparse spatiotemporal observations. And they use the state-of-the-art machine learning approaches, right? And what the slide is showing you that if you bring in the KGML machinery, which actually treated this as a system in which there's a forward modeling and there's inverse modeling going on, and then you sort of jointly model them together to give you a new meta-learning framework, which is the last line. And the beauty of this last line is that it's able to give you much smaller errors with much less data. Okay? So again, the power of combining scientific knowledge and machine learning to improve this auto sample performance. Another example, this is with the prediction of river forecast, the hydrological forecast prediction that is made by NOAA, literally on a routine scale. The entire country has about a dozen or so NOAA operational centers. One of them happens to be in Minneapolis, which is responsible for about 5 state regions. Literally, there are hydrologists, each responsible for a couple of catchments, couple of areas. And you see one of those regions here up in the figure. And their job is to every day, in the two times in a day, you make forecasts. What's going to happen? And of course, they miss some. They try to do their best. And what this slide is trying to show you is using this methodology, this variations of methodology I talked about. When you're sitting at day 0 and you're making prediction for the next 7 days, right? Day 0 is today, right now. Every dot is every 6 hours, right? The stars are the observations, because if I go back 2 months ago, I can see what happened 7 days afterwards. The blue line is the machine learning. The red line is a machine learning algorithm, which is competitive, at least as good as the physical model. The yellow line is the machine learning algorithm that assimilates data as good as the best assimilator of data, yellow line. And the blue line is this new KGML framework, which models the processes at different scales and allows it to assimilate information in real time, gives you the blue line. And look at this, I'm studying at time 0, and it's able to make the prediction of the forecast 6 days ahead and exactly how it's going to go up and come down. So pretty amazing performance. Shashi talked about the similar methodology underpinning the being able to convert agriculture from greenhouse positive to greenhouse negative. And again, this graphic here he showed yesterday, illustrating the same thing. The dots are the observations of greenhouse gases, and all the other lines are physical models, and pure machine learning models are the other lines, blue and the green. And the red line is the KGML line, and it sort of gives you a really, really good prediction. This work was just appeared in Nature's Communication just a month ago. This is going, I mentioned to you the ability to model all of the ocean eddies on a global scale. There's another project that we started about 10 years ago, which was being able to model all of the water bodies. And we were at that time focused only on areas below 50 degrees, which is where most people live. And it created the first of a kind water body data set and its dynamics, how it's changing on a monthly scale. And it was sort of publicized very widely. There were at least 3 dozen outlets around the world that covered this news. But I'm more excited about telling you about something that's actually going on, because at that time, we were looking at the places where people live. And right now, if you look at the top right corner of the world, we're looking at the poles, because as we started collaborating with our friends at University of Alaska Fairbanks, right here, Katie Anthony, which happens to be actually from Minnesota, but is a faculty member here. She spends summers at Minnesota, so which is why she's not here, right? And you look at, so this methodology, again, a knowledge-guided machine learning methodology, has been built to map all of these polar lakes in the upper region. And I'm just showing you example of just that little top right corner there, expanded here and expanded here. And again, this is being able to take this data, use the similar types of methodologies that people use in foundation models, except that now it's driven by the scientific knowledge, and build these maps sort of automatically. This work is not published yet, but it's being prepared for publication. This slide has a whole bunch of other things. You see the top right, the ocean eddy simulation. This was, again, the data set produced for the first time of 20 years of ocean eddies published in Nature Climate Change. Again, this was about 9 years ago. Some of the other works from the expedition, top right corner, on agriculture, again, feeding into the AI climate, and some of the other things that you have seen here. Some of the other results that came out of the bigger expedition project and the featured in various things. I mentioned to you about this AI-enabled scientific revelation workshop that NSF asked us to hold at their headquarters last year. And again, with the sole objective of revolutionizing AI with science as opposed to with what's going on right now, and vice versa. So with that, I would just like to conclude that there is a tremendous opportunity for, if you are a computer scientist, big data person, to increase understanding of our Earth's climate environment. But these problems have unique challenges, and we are not just solving them, but we are learning from them. So it's a two-way street, and it happens only in the context of projects like these in which people are working together. And these methods are actually being used now in every single discipline that you can imagine. 2 years ago, we published a paper on ACM computing surveys, reviewing what happened in the previous 4 years. And it turned out there were about 400 papers, all published in the 3-4 years past on this topic. And they covered every single discipline you can imagine. So this is an area which is very, very exciting, and everybody's working on it. I'd like to thank my students, collaborators, and all the different agencies that funded this work. Thank you, and I'm happy to take questions. Yes.
Great talk. Thank you. Yeah, I've got questions about your lake finding, but I'll ask those later. But I was just curious, in the big picture, like obviously the various projects you and your groups are working on, what are the sort of problems you're tackling right now that really that are challenging your models? You've showed a lot of successes here, but like, what are the things you're really scratching your heads about right now, and that are sort of hitting the boundaries of what your models can currently do?
It's a treasure trove of challenges, right? It's a treasure trove of challenges, and because if the problems are easy and we solve them, we'll be happy because we are happy in the humanity, right? That's what I tell the students. But if you're not, then you should not be sad. You should say, hey, there's a problem for me to solve, right? And of course, there's a problem everywhere. You remember, this is a journey, greenhouse gas emission, Shashi talked about. This is the institute. We have a success story on a farm that we can do this, right? But being able to convert it on a global scale, what we're doing here, does it work in Texas? Does it work under different scenarios that we can observe, right? So the story that we mentioned that served as the proof of confidence for the institute took data from certain locations in Midwest, and this data had observations, and we sort of say use part of them to build a model, machine learning model, process guided model, and KGL model. And then we went to the other locations and sort of say, hey, look, we don't have any information, and we can do a better job, right? We can do a better job than pure process model. We can do a better job than pure machine learning model, but we look good because they were so bad, okay? But there's a big gap in where we are and where we need to go. That's one part. The other part is all you can sort of say that we have shown there's a hope in handling the heterogeneity in space and time, but it's a big, massive problem, right? So I mean, there are students doing dissertations, and each one is sort of hitting on the next problem. And we, as we understand, as we run work on this problem, we learn something new. I mean, I mentioned to you the ability to handle formulations at different scales, right? This one, right? I can show you my slides going back 7 years. I would put that thing, hey, we need to model phenomena at different scales and time, right? The first time we could do this was in this context of this problem. It happened through a conversation. These guys were there in Minneapolis. We were talking, and they were talking about saying, hey, look, if we make the forecast, we are hydrologists. We know we are responsible for these 3 river catchments, right? So we will fly planes, we will fly drones, we will drive around to see how thick the snowpack is, or take the soil sample, so you can sort of tell whether my forecast is going to be good or not, right? Well, that forced us to think, hey, could we bring the machine learning algorithm to do the same thing? And of course, the machine learning algorithm cannot go and take samples, right? But it could look at what happened in the past and figure out these underlying states and model them. And through the dialogue, the collaboration, this thing came up. And now this paradigm is very general in the sense that you could use it in any situation where you have multiple processes at different scales, number one. Number two, where you have the need to model and assimilate data. So what I'm trying to say is that I would say we have scratched the surface, and there is tremendous amount of work to do, and it's just excitement, right? In the sense that either way you win. If you solve the problem, you're happy. If you can't solve the problem, you're happy because you have a challenge to pursue. Yes.
Thank you, Vipin. This is very inspiring. I was wondering, in terms of observations that you talked about, can you use machine learning to identify which regions are sensitive in terms of prediction, send drones or send observation platforms to go observe there, and then assimilate that into the model to improve it.
Absolutely. So you're sort of referring to dynamic active learning,
Right.
right?
Yeah, exactly.
So the idea,
With the real world.
and it's a problem that's not solved yet, right?
Yeah.
But when I talk about this system here, going from highly observed to unobserved, so I mentioned to you two things. If you go to unobserved, the paradigms exist that would work with even unobserved data, okay? But they're not as good, obviously, right? If you have some observations, they could get much, much better, right? And that's where your comment applies. That is, could I figure out what is the uncertainty in places where I need to make the observations, right? And that's a very active area of research, right? And so yet another problem in which I would say no progress had been made, but tremendous work needs to be done, because the traditional approaches people use for active learning, there's a big community, they don't apply. And there's a tremendous approach there. So yeah, you work with a scientist and you come up with troves of problems, something that you would never think of when you're working on the traditional MLAI applications.
Thank you.
Yeah, great comment.
Thanks for the great talk. Can you maybe next 2 pages to 21? I think you page
The previous
to 21. I think you were saying this. Yes, 21. Yeah.
Oh, sorry, I'm going the wrong direction.
You were talking about the study showing this scientific data talking about the sparse spatial temporal observations. I think this is a very common challenges for spatial temporal data. We just have it so expensive to collect the ground truth. So can you summarize a little bit more on how this the model can work with this limited ground truth data?
Perfect. Great. Again, this is just a model problem in computer science, and this is meta learning is an approach. The method you see, MAML and multimodal MAML. If you look at the meta learning literature, you'll find thousands of papers written by the machine learning communities, right? Okay, and they would do, as you sort of said, look, you have the data from the past or data from some entities. You build a model and then you transfer it to the other entities, right? This is the MAML is, if you go look at how many citations, I think there'll be like 10,000 citations to this paper, right? Because so many people use this methodology. Then people have multimodal MAML, and these are all purely machine learning models in the sense that there's no science involved in them. So the last line is what you're sort of saying, how did science get involved in, right? So the first two lines are simply sort of saying, give me the data, I will try to build a relationship between the drivers and the response. Actually, they just say, give me X and I'll build a model to Y. I call them drivers and response because I'm looking at an environmental system, right? So when I do that, I sort of say, hey, there's a forward model that I'm trying to build, right? But then I could also try to build the inverse model that is given the data, I can also build the characteristic. So what you see here in the top right corner in the middle is the upper portion is the forward, lower portion is the forward model, and the upper portion is the inverse model. And in the TAMRL, you're actually learning them simultaneously. So you have whatever observations you have in the top right corner in highly observed regions, you learn the forward and inverse model jointly. You go to less observed regions and use whatever data you have to keep the forward model as the same, but use the inverse model to figure out what the parameters are. And when you do that, by way of doing it, using even 1 month of data, you can get an error like 2.33, which is of the same order as, but if you have lots of data, like 24 months of data, you get even much lower error. So if you look at the columns are different months that you are using data from, and the numbers are, of course, the error. And you can sort of see this last line, which recognizes that the phenomena that you're trying to model actually can be viewed from the both forward and inverse angle. And if you model them both simultaneously, you have more information as opposed to building just a meta-learning approach or a multimodal meta-learning approach, which neither of which recognizes this phenomena underneath. And by recognizing that there are special characteristics of the system, you should try to build them, even though you don't know what they are, but you're trying to reconstruct them, right? So it's just like the embeddings. Embeddings always do magic because even though we don't know what they are, but they really have an impact, right, on something. So the embeddings are being treated as the characteristics, and I am trying to make sure that both of my models work, right, forward and inverse. And when you do that, the whole modeling gets much better, and the meta modeling gets much smarter. And again, the papers have a lot more detail, right?
Thanks for bringing this fascinating topic to the meeting. It's really a great way to start off the day. Have you given any thought to taking all of this work together and creating a foundation model for environmental science or thoughts?
Huge work is in progress. Of course, not in our group, but also everywhere else as well. When people sometimes think of foundation model, they think of ChatGPT. But what they should really be thinking about is this paradigm that's listed here, right? That is, you have some places you can collect, you have data in the green spaces. You could learn from it. And then you can go to a place that is different and you have very little data or no data. And so this work has been going on in the environmental science community, in our group and other places for 7-8 years, right? In this direction. But this is the underlying methodology of foundation model. So what I'm trying to say is that yes, we are doing the foundation model, but we are doing it not because foundation model showed up yesterday, but it's the same methodology. That is, you leverage what you have, and then you go to a new scenario and work with it. Somebody made an observation early on. Remember the image, some of the first successes of deep learning, the revolution that you see today, came in the context of ImageNet. The convolution neural network that everybody's so fond of were invented actually in 1989. Okay? Nobody paid attention to it. Okay? Because these were the groups that sort of working somewhere, nobody cared about them. By about 2010 or so, around 2010, these guys say, hey, look, maybe we want to show that these other people too that it's working. So some of them in the visual community just sort of said, hey, look, this ImageNet has come up. It's a very large data set. If you could work on it, then come back to us. They're thinking that they will work on it, they will not get anywhere, and they'll get lost, right? Okay. So it sort of course, it worked, and you see the entire evolution that we would not be talking about today. We will still be using AI science, but perhaps not in the same way, right? Okay. But that required a lot of data. Somebody made the observation that a kid, a computer program needs millions of images to figure out if it's a cat or a dog, right? But to a kid, a newborn kid, 1-year-old kid, you show them a cat, they will know a cat, and they will look at a different cat, they'll say this is a cat, right? In the sense that it's a human child, very, very young child, would sort of, oh, cat, right? I mean, one example with them. And that's exactly sort of what's happening in these new revolutions. That is, the kids start learning the moment they open their eyes. So their brain is processing data continuously, right? And when you give them one example, they learn from it. So this idea of learning from a lot of places where you have data and going outside with a few samples, this is a paradigm. If we didn't have that, we would be helpless. So this is what sort of underlies, of course, foundation model. This is what underlies the idea of self-supervised learning, which you heard a little bit about yesterday. And this, of course, is a component of KGML in the sense that these are the best practices in machine learning that you have to bring in, except that you can enhance them with scientific knowledge.
May I ask? Oh.
Hi, great talk. And I apologize in advance if my question is not properly formulated, but something we struggle with in ice sheet science is that we try to make projections and the future looks nothing like the present or anything that's been observed so far. Like the Arctic is going to be ice-free in the summer over, our lifetime. The ocean is getting warmer. There has never been as much meltwater at the surface of the ice sheet. How do we deal with conditions that are not part of the training set?
Exactly. And again, as I said, that's the first challenge our community has to face. And if we don't, we shouldn't be coming back to you, right? And this is what this was just one example of showing that, right? Okay. So the idea is that science can transcend scenarios. It's not complete. I mean, your representation is not complete, but the law of physics will not change. Okay? But the machine can do a much better job of finding patterns in the data. Right? So what you're seeing here on this example is that here is this process model, which was trying to represent, it has the right physics, but there are so many parameters in the physics, they did not get calculated well because you didn't see it there. So this purple version actually learned most of the physics from this one. I didn't show you exactly how we did it, right? So basically, the purple one had access to all of the synthetic data generated by this green model, which is imperfect. But yet it learned enough about the summer and winter and spring from that one, right? But then it calibrated it, it modified it using the other 3 seasons, right? And it became worse too, but not that much. So what this tells us is that there's a hope in bringing the science and machine learning together to address this challenge. That is the biggest challenge, because even here, there is no guarantee that KGML has learned everything. Okay? So this is where the journey is, right? In the sense that somebody says, can you solve all the problems? No, this doesn't say you solve the problem. This simply says that we have a hope of making a dent in this stuff. Yeah.
Yeah, thanks for the broad overview of 1 billion papers I'm not going to read because I have to read about ice. And so I think following on Matthew's question, is there an example to, well, let me put it this way. When the machine learning does better than the physics-based model, that tells you that there are patterns in the data that aren't being captured, which means that the physics-based model is missing something and needs better physics. Are there examples where that mismatch has led to better physics-based models? Because I think that's where we sit, because we need the physics-based models in order to go into the future with confidence, because the future doesn't look like today, so we can't train on it. So in my mind, the machine learning that does better than the physics-based model is telling you that you need to improve the physics-based model, because we need to get to projection into space that machine learning doesn't know about yet. So are there examples of that where the physics-based model now, the formulations, the weights in it, the solution of it has changed?
Excellent question. Excellent question. And I put a bullet early on saying that even if the machine learning models solves all the problem, right? Science is not advanced. If you talk to the people from linguistics, there's a huge area of linguistics. They are very upset at the fact that these models are so good. You could take your phone and go to any language and translate it and do a pretty decent job, right? And using their methodology, you can't do very much more, right? Okay, you can't do much at all. But the science advances by layers and layers of our understanding. And the question is, how does this community of data scientists, with or without scientific knowledge, advancing the frontier, right? And I can give you anecdotes, and I'll give you an anecdote on this very first example, right? Because it's a very powerful one. Because it applies to, your statement applies here. So even if I don't have the KGML model, right? Suppose I assume that I have what I have, right? So you can see that the orange line is superseding the green line if you have a lot of data, right? So the observation applies there. Now, because this was a model case that we were studying very, very carefully, we noticed that both KGML and the orange line, both of them, see, we are trying to measure the temperature of the lake at different depths, like at 50 different feet, we're looking at temperature at different depth. So it turns out that all of these models were doing a really good job of predicting the temperature at the surface of the lake. Because the surface of the lake is driven to a great extent by the weather. If it's cold, surface will be cold. If it's warm, surface will be warm. If the day is a little hotter today, the surface will get a little bit warmer today, right? Things like that. But the dynamics of how the water temperature changes underneath is much harder, right? So what we were amazed was that both of this purple line and the orange line, the machine learning with scientific knowledge and without scientific knowledge, they were actually doing a better job of modeling the temperature at the lower depth, certainly the KGML, right? Okay, so then the USGS guys sort of said, these are the guys who sort of, the deep into building this model. They sort of said, and here's the kicker. The modeling of the temperature at different depths actually is a much more complex problem, because they have this thermocline shift. In the winter, the water is warmer on the top, and in the summer, the water is warmer at the bottom, right? And this incline changes, right? Because as you go from one season to the other. And KGML was doing a far better job of capturing it. And most of the improvement that you're seeing here are coming from the depth. If I only report the improvement on the depth, the numbers will be much more divergent, in the sense that it'll be KGML will look much better, right? And they sort of said that means clearly that the way that they are modeling the physics in GLM has some very serious deficiencies, right? So they still don't know how to model it better. And probably modeling it better is not a good idea because that will create even more parameters. And even with the parameters they have, they can't really calibrate it good enough. But it's the example, it's a close example I can get to.
So there are some questions online as well. I know we're running out of time, but I want to at least take one online question. So Amal asks, one major challenge I see in the complexity of integrating machine learning and knowledge from the physical model. Are there any initiatives to tackle this problem from a software engineering point of view with generalized frameworks?
Great question. Great question. And I would sort of say we are still in the trenches trying to figure out the bits and pieces. And eventually, when we have enough of those, I think then we will need the help of the software engineering community. Great question. I haven't thought about it, but thank you for making me think in that direction.
Wonderful. I saw other questions online as well, but just in the interest of time, we'll take some of those questions and share with you if that's okay. But
Oh, yeah.
let's thank Vipin again for a wonderful talk. Thank you.
Thank you.
I'm sure there'll be more conversations with you while you're here. Okay, so we have a quick break till like 10:15. So let's take a short break and then we'll come back. What time is it right now?